Hello, in this video we're going to talk about solutions, their concentration, and dilution. So first, some vocabulary. A solution is a homogeneous mixture of two or more things, and by homogeneous we mean you cannot tell the components apart except on the molecular level. And in this mixture, the solute is the substance present in a smaller amount, and the solvent is the substance present in a larger amount. So a memory trick, to remember which one is present in the larger amount, solvent has more letters than solute, so you can hopefully keep them straight that way. This is definitely a definition you need to know, and it's a very commonly used set of definitions throughout chemistry. So as an example, say you had a packet of Kool-Aid, and you dissolved it into water. Well, your solute in this case is Kool-Aid, starts out as a solid. The solvent is always a liquid, in this case water. And then you make a solution, in this case Kool-Aid, the drink. And while we're on the subject of Kool-Aid,
I'm sentencing you to 24 months in prison.
Oh no.
Oh no. Oh no!
Oh no.
Oh yeah!
okay, so scientists have a need to measure the concentration of a solution and have units that describe how concentrated a solution is. The unit of choice in chemistry is molarity. So we call the concept molarity, but when we describe the unit, we'll just say the word molar, like this is a 2-molar solution. And molarity and molar are abbreviated with a capital M. So the molarity is the moles of solute over the total volume of the solution in liters. Now this is total volume, so if you have some amount of liquid and then you add a bunch of solute to that liquid, you may expand the total volume of the solution. For small amounts of solid or other solutes, that's probably not going to change your volume too much, but if you're making a very concentrated solution, it might. So, if your solution expands after you mix it all together, well then you need to know the new total volume after it expands. So that's why we make a big deal about this. And if you want a formula to describe molarity, you can say it's number of moles lowercase n over total volume V. So an example, what's the molarity of a calcium chloride solution where you have 0.7 liters total volume containing 1.27 moles of calcium chloride? Okay, so remember, molarity, capital M, is moles of solute divided by liters of solution. So we have the moles divided by the liters, and this equals 1.8 molar. Now notice the problem was stealthily phrased to say, what's the molarity of a 0.70 liter solution, which implies that this is the total volume. Okay, now that we know that we have 1.8 molar calcium chloride, what is the molarity of calcium ions in this solution? So assume that calcium chloride is a strong electrolyte. And what that means is that when you take calcium chloride, solid, and you put it in water, you get calcium ions dissolved in water, and the calcium ions split from the chloride ions, which are also dissolved in water. So we say aqueous for dissolved in water. So your calcium and your chloride split apart when you put them in water. This is the definition of a strong electrolyte, and this is what any ionic bond does when you dissolve it in water, so what any salt does. Okay, so if you have 1.8 molar calcium chloride, that means you have the same concentration of calcium ions in solution, but for every calcium chloride you make 2 chloride ions dissolved in solution, so then you would have 3.6 molar chloride ions. At the moment we haven't taught you about strong electrolytes yet. That definition will come later, but I wanted to include it now for completeness. Okay, another example. What's the molarity of a 511 milliliter solution containing 205 milligrams of ammonia? I encourage you to pause the video, try this problem, and then resume to hear the answer. Okay, so for the solution, we're going to try to find molarity, but we need moles over liters to do that. And right now, we don't have moles of ammonia, we have milligrams. So we need to find the number of moles of ammonia. So okay, we have 205 milligrams of ammonia. Now to get that into moles, well, we first have to convert milligrams to grams. Why do you have to do that? Well, because the molar mass of ammonia, 17.031, is listed in grams per mole. So we start with milligrams. We have to convert milligrams to grams first. And remember, you put the milligrams on the bottom so that your milligrams cancel out. And then when you use your conversion factor relating to the molar mass, you put the grams on the bottom so the grams cancel out. And this equals 0.012037 moles of ammonia. If you're doing this problem from scratch, you'll probably also have to separately calculate the molar mass of ammonia, which I omitted that calculation here, and instead I just gave you the result. Okay, so now to find the molarity of this solution, you first take the moles of ammonia and divide it by the total volume in liters. So we have 0.012 moles of ammonia divided by 0.511 liters of solution. And now I made a shortcut here too. So what I did is I said 511 milliliters times 10 to the negative 3 liters are in 1 milliliter. And then this equals 0.511 liters. And then I took this number and put it up in here. So we have moles of ammonia, liters of solution, and that gives us our end answer, 0.0236 molar NH3. Now let me describe how to prepare a solution in the laboratory. So first you weigh out your amount of solid. This is assuming you have a solid solute, which is not always the case. You can have an aqueous solute or even a gaseous solute. But if you have a solid solute, the first thing you do is put that into a device called a volumetric flask. So here's your solid at the bottom of the volumetric flask. And you weigh that out so you know how much solid you have. And then you pour water in and you fill it up so that the water is right at this line on the volumetric flask. So this is the whole point of a volumetric flask. It's designed to very precisely hold a calibrated amount of water. So it will hold 100 milliliters, 25 milliliters, something like that. And you can get them smaller or larger as well. In chemistry, you take the meniscus and put the bottom of the meniscus at the line on the flask. So let me show you what I mean. So I'll zoom in and make a drawing of the neck of the flask with the line that's etched into the flask. And so when you put water into this flask, it will form kind of a U-shaped surface because the water is attracted to the glass. And so it climbs the walls of the glass a little bit. And all of the glassware in chemistry is calibrated such that you put the bottom of the meniscus on this line. And so down here is where all your water is, etc., etc. So you put the water into the flask such that the bottom of the meniscus is at the line. Okay, so once you make a solution, so oftentimes you wind up diluting it, and so we really need to know how to calculate how the concentration of a solution changes after you dilute it. You have experience with this in everyday life. If you were to make concentrated Kool-Aid and then pour a bunch of water in it, you now have diluted Kool-Aid, and you have less of the Kool-Aid flavor and dye molecules in a given amount of volume, so thus the concentration's lower. So that's the definition of a dilution. Now, this picture is a little hard to see, but it's showing that if your volume is, say, only this big, and you have however many moles of solute in this volume, now if you add more water to it and you don't add more solute, well, now you have the same number of moles of solute, but you have a much larger volume. So therefore the concentration, which is moles per volume, per liter, is going to be lower when you dilute. To go the other way, you would say you concentrate something. That's a lot harder to do experimentally, so usually we wind up diluting things. So we need to know how to calculate what happens to the concentration after a dilution. So the big key here is that the moles of solute is constant throughout the dilution. You're not adding or removing molecules of solute, you're just changing the volume of solvent in which they're dispersed. So one way to think of this is, for the initial concentration, if you take the definition of molarity, which is moles over liters, and then you multiply that by the volume of solution at the time in liters, then this will give you the moles of solute as your outcome. Now, this can be rewritten as m times v equals n, and I put subscript 1s here to say this is the initial concentration. So m1 v1 equals number of moles. Molarity times volume gives you moles. Now, after you dilute something, if you take the molarity and multiply it by the volume, it will still equal the number of moles, because this is true all the time. And before and after a dilution, well, you have the same number of moles of solute. So this N is the same for both cases, so you can set these equal to each other and say that M1V1 equals M2V2. So what this says is that the molarity and the volume before the dilution is equal to the molarity and the volume after the dilution. Okay, again here, V is the total volume, solute plus solvent, plus any water you added to it during the dilution. So an example, how would you prepare 60 milliliters of 0.2 molar nitric acid, HNO3, from a stock solution of 4 molar nitric acid? So first let me say what a stock solution is. Literally it's a solution that you stock and keep around to then make your samples from. So it's convenient in the lab to make a more concentrated solution and keep it in a bottle on the shelf, and then you can take little bits of the stock solution and dilute them with water to make various samples of various concentrations. It's much more convenient to do it that way than to make up a new nitric acid solution, say, each time you want to use it. So that's why it's called a stock solution. So say you have a 4 molar stock solution and you want to make 60 mils of 0.2 molar nitric acid. So here's the formula for dilutions, M1V1 equals M2V2. I'll give you this formula on the info sheet of a test. So it's helpful to list out what pieces you're trying to use here. So M1 is 4 molar, and it doesn't matter what you decide, which one's case 1, which one's case 2. So just pick one and be clear that the right molarity and the right volume go together. So I'm going to pick the first case is the stock solution. So M1 is 4 molar, and we don't know what volume of the stock solution we'll need to take out of that bottle. So that's the thing we're trying to solve for. Then M2 is 0.2 molar, that's what we're trying to make, and we're trying to make 60 milliliters of that. And so I did the work to convert milliliters to liters already, so it's 0.0600 liters. So we're trying to solve for volume. So we can take M1V1 equals M2V2, rearrange it to solve for V1, and then we plug our numbers into this that we just laid out. And then this equals 0.00300 liters, which if you convert that back into milliliters is 3 milliliters, 3.00 with 3 sig figs. Okay, so you'd use this math, you get the number 3 out of it, 3 milliliters. What does that mean? So that means you take 3 milliliters of the stock solution, and I should write the word stock solution in this sentence, and you dilute it with water to reach a total volume of 60 milliliters. So this means that most likely you're adding 57 milliliters of water plus the 3 milliliters of acid to make 60 total. Now to be fair, I said water here, but up in the description at the top, I don't mention what the solvent is. You could do this exact same math if your solvent is something other than water. I don't have a good example of what nitric acid would dissolve into that's not water, but the math would work if it was some other liquid. However, in general chemistry, we typically assume that everything's dissolved in water, just because we're not dealing with other solvents, really. So I just made the assumption there. So that's what we have for solutions, molarity, and dilutions. Again, this is something that we use all the time in chemistry, so please take the time to learn it and understand it now, and you'll be set. Thanks again.